Greetings, CSE158 staff, teachers, tutors, TAs. Our project is specifically about predicting review helpfulness in the Amazon Fine Foods dataset. And along with me, this project includes Angela Yuan and Victor Chen that we all worked together on. And so for our predictive task overview, our task is to determine whether an Amazon Fine Foods review is helpful and reformulate this as a binary classification problem where the output label is underscore helpful, either 1 for helpful or 0 for not helpful. And in the dataset, helpfulness is defined using the helpfulness ratio, the number of helpful votes divided by total votes. And if this ratio meets the dataset's threshold, the review is labeled as helpful. The motivation behind this task is pretty practical. Platforms want to surface reviews that are genuinely useful, and if we can reliably predict helpfulness, we can highlight high-quality reviews, improve user experience, and potentially reduce misinformation or low-value content. So at a high level, our model takes in a review's text and metadata as inputs and outputs a prediction of whether it's likely to be perceived as helpful by users. So for helpfulness label definition, a review is labeled helpful if its helpfulness ratio is at least 0.6 and has 3 plus votes. This gives us a clean binary target. We evaluate using accuracy, precision, recall, and F1, with F1 being the most important because the classes are imbalanced. So for the baselines we used, we started with very simple models to establish reference points before moving on to more complex approaches. The first being the majority class predictor, which always predicts that a review is not helpful. This gives us a true lower bound and it helps confirm that any real model is learning more than just the class imbalance in the dataset. The second baseline was logistic regression with TF-IDF text features. It's a classic baseline in text classification. It's fast, interpretable, and strong enough to give us a meaningful point of comparison for our more advanced models. Together, these baselines help us understand how much performance improvement we gain as we add richer features and more sophisticated models. So our dataset uses the Amazon Fine Foods, which has about 568,000 reviews. Each review comes with useful metadata like the product ID, reviewer ID, star rating, review text, and a hopefulness score. This richness makes it a strong dataset for both NLP and recommendation tasks. And the example at the bottom shows the raw format we worked with before pre-processing.
This is the EDA, helpful versus not helpful reviews. This slide shows the distribution of our target labels. Most reviews in this dataset are labeled not helpful, which means the data is imbalanced. Because of this imbalance, accuracy alone can be misleading, and that is why later on we rely on more precision, recall, and especially F1 score to evaluate how well the model identifies helpful reviews. And this is the EDA for numeric feature distributions. This slide shows the distributions of our key numeric features, especially the helpfulness ratio. You can see that many reviews cluster at 0 and 1, which means people often give either no helpful votes or unanimously helpful votes. This skewed distribution reinforces that the dataset is imbalanced and that the numeric features alone may not fully capture helpfulness. It also helps motivates why combining text features with these numeric signals is important for modeling. And this is the EDA for rating versus helpfulness. This plot shows the distribution of star ratings for helpful versus not helpful reviews. The two groups look very similar, which tells us that the rating by itself doesn't strongly predict whether a review is considered helpful. This reinforces the idea that we need text-based features and additional metadata, not just star score. For pre-processing, we first executed the helpful and total vote counts and computed the helpfulness ratio for each review. Using that ratio and a minimum vote threshold, we created our binary target label, which is underscore helpful. We also added features like review length and remove entries with invalid vote data. Finally, we vectorized the review text using TF-IDF with unigrams and bigrams. The small table at the bottom shows an example of what clean dataset looks like.
Okay, so for context, here I'm showing how we formulate the helpfulness prediction task as a machine learning problem. The inputs are the TF-IDF text features extracted from the raw review text and numeric metadata features like helpful votes, total votes, helpfulness ratio, and review length. And the output is a binary label, which is underscore helpful, which tells us whether a review meets the helpfulness threshold defined as helpful underscore votes divided by total underscore votes and checking if that's greater than or equal to 0.5. But because the dataset is imbalanced, we use a linear SVM with class-weighted training, and we optimize for F1 score using cross-validation to get good performance on both classes. And to walk through our code, we first begin with data cleaning and feature engineering with the pipeline and a fresh new copy of the dataset, which is df underscore model. And from there, we compute the fixed types for star rating, review length, and date time. And then we create the readability flesh column, which helps us capture how easy a review is to understand, which in turn influences perceived helpfulness. And then after that, we compute for each product average rating, variance, and the number of ratings, and then from there merge them into the main data frame. And then we create the rating deviation, which is just the review scores minus the product mean scores, as well as rating extreme, which is the review scores with 1 out of 5-star reviews. And here we just create the full input matrix, and we create the tree and test split, and we use stratification to help preserve the class imbalance structure. And from here, we create the column transformer, which applies the TF-IDF to the text column and the standard scalar to the numeric columns. And after that, we wrap preprocess plus SVM inside a pipeline and tune it with the grid search. And so here are all the models we worked with, and we want to check like which models worked and which didn't. And so beginning with the baseline model, it's the length only logistic regression, which basically gave us no predictive power. It kind of just confirmed that we need more than just simple heuristics. And our text only models performed better. So we worked with the TF-IDF with logistic regression, which gave us a good, strong classical baseline, and TF-IDF with linear SVM improved recall by handling high dimensional text more effectively. But they were both still pretty limited because they only relied on text. Performance jumped once we added numeric metadata. Our mixed feature model showed that review context like product rating behavior helps the classifier, even though we had to remove leaking features for fairness. And the strongest results came from the hybrid SVM models. TF-IDF combined with safe numeric features and the balanced SVM gave us much higher recalls for helpful reviews, and after tuning with grid search, our optimized SVM became the best overall model, achieving the highest weighted F1 and the best accuracy recall trade-off. So for this slide, our final model is the optimized TF-IDF plus numeric features plus linear SVM. And so let's break down what its parameters actually mean. In an SVM, every feature, whether it's a word from TF-IDF or a numeric variable, gets a learned weight. These weights tell us two things. First, whether a feature pushes the prediction toward helpful or not helpful, and second, how strongly it pushes it. A positive weight increases the predicted helpfulness, while the negative weight decreases it, and the magnitude tells us how impactful that feature actually is. On the TF-IDF side, high weight words usually reflect signal phrases that helpful reviews consistently use, things like explanations, comparisons, and descriptive detail. Meanwhile, low weight or negative weight words tend to be more vague or generic. And so for numeric features, each one has a standardized weight after scaling, which lets us interpret broader review patterns like longer reviews, clearer writing, and more textual detail, which tend to push predictions toward helpful, while very short or extremely emotional reviews push the other way. Product level context features like rating deviation or variance also carry meaningful weights, captures how typical or atypical a review is for that product, which ends up helping the model distinguish genuine insight from noise. Overall, these parameters helps us see not only what predicts helpfulness, but why. And from here, interpreting the model led to several interesting takeaways that actually match real world behavior pretty well. First, review structure matters more than emotion. Length, readability, and concrete detail were much more predictive than whether a review sounded positive or negative. People reward clarity and usefulness, not just enthusiasm. Second, adding context dramatically improves prediction. Product level features like mean score, variance, and rating deviation help the model understand how each review fits into the broader pattern for that item, making the predictions more stable and interpretable. Third, the TF-IDF weights tell us a really clear story. Helpful reviews consistently use examples, descriptions, comparisons, and specific reasoning. Unhelpful reviews tend to fall back on more vague language like good, bad, or I liked it. And finally, the model actually confirms real world intuition. People upvote reviews that teach them something new, offer clarity, and provide useful detail or include evidence. In other words, helpfulness isn't really about emotion, it's about information. These insights not only guide model design, but also reflect broader behavioral patterns in how people judge the quality of online content.
For evaluating our model, we focused on metrics that make sense for an imbalanced classification task. We report accuracy, precision, recall, and F1, but F1 is the most important because it gives a balanced view of how well the model identifies helpful reviews without being misled by the majority of the not helpful class. We use a train test split to measure generalization. In our case, we use a stratified split so that the proportion of helpful and non-helpful reviews stay consistent across both sets. This make our evaluation more reliable. To pick the best model, we use grid search CV, which lets us systematically test different values of the SVM's C parameter and select the one that gives the highest F1 score on the validation fold. Overall, this setup ensures that the performance we report is both fair and optimized for the goals of the task. Right here, we have the actual code we use for the evaluation. We first define the pre-processing pipeline, which applies to the TF-IDF, to the text, and scaling to the numeric features. Then we wrap that into a full SVM pipeline. Grid search CV runs this pipeline across different C values and picks the one with the best F1 score. The last line fits everything on the training data, ensuring pre-processing and modeling happening together in one consistent workflow. Here's is what we're looking at the results for the best performing model, which combines the TF-IDF text features, numeric features, and readability features using a linear SVM. The overall accuracy comes out to about 70%, but the more important metric here is that the F1 score for helpful reviews, the minority class, is about 0.57. The classification report shows that the model is noticeably stronger at identifying non-helpful reviews, but it still does a reasonable job detecting helpful ones despite its imbalance. We also compared this model against simpler baselines like predicting the majority class, numeric-only models, and TF-IDF with naive bias. Our SVM model clearly outperformed those baselines on precision recall and especially F1. Finally, the confusion matrix and detailed report suggests that adding readability features didn't actually improve the model's performance and may have made the model more